This presentation is on design quality maturity measurement and how to use such a measurement as a field return rate prediction tool. The presentation will explain in detail the importance of design quality testing and the use of design maturity measurement as a KPI to be used within the R&D function. The presentation forms the first in a series of 4 presentations in managing and predicting product reliability to manage and minimise service cost allocation. Now, a DQA or Design Quality Assurance Test and Design Maturity Improvement Programme is all about first putting the DQA test methodology together, and you need a strong DQA test programme to find major issues before mass production. If we don't have this, then there's a high likelihood that we'll miss many design quality defects, especially in early mass production. It will take a long time, 6, 9, 12 months to get field data back, issues from the customer to understand what are the issues and how much can be attributed to bad design quality. Now, a strong DQA test program with design maturity controls gives the producer the opportunity to control release of a new design and make objective decisions based on percentage design maturity level, rather than basically just talking about issues, when they'll be solved, and hoping things are going to run well. It gives all of the management engineering team a way of controlling and measuring how the design is progressing throughout the cycle. Now, the appropriate design quality test maturity measurement model will basically always directly correlate with verified field return rate levels, and so the maturity measurement can be used as a very strong design field return rate prediction tool, which is the key emphasis and the key purpose of this presentation. The DQA testing is all about performing a range of pretty high accelerated stress level type tests, not just thinking about using them within the specification limits as you see on the small diagram. It's to understand what the design limits are from a functional and stress point of view, individually and both combined, but to make sure we don't overstress the product or the sub-assemblies into destruct limits and cause defects. We want to stimulate defects. The old way of trying to simulate field performance is no longer. Designs are far too complex now to do that successfully. So simulating complex electronic or electromechanical products and trying to simulate the field performance and the type of defects exactly is almost impossible. We've got to look at trying to stimulate defects with a range of different types of design quality tests, functional and stress tests, and allow this to help us to improve reliability by investigating through this testing what the defects are, which ones to resolve, and not to avoid testing and missing issues, which often happens. Now, the DQA testing design maturity model, we've got to calculate design maturity. It's a key measurement, and it will come from a well-organised design quality test program. We do a wide range of testing depending on the product, and we have to make it very specific to the product type, but not all these tests are equally effective in detecting latent defects. Different tests are therefore given different weightings to represent their effectiveness. These can be critical, major and minor, will all get different weighted scores. As weighted levels of each test accumulated, the design quality test program forms an overall target score, and any time defects are found and not fully resolved at any point in the design cycle, a score loss is the result. We can see from this example there is a range of environmental tests, mechanical tests, also electrical tests, all of which combined, when we've got their weighted scores, add up to an overall point score of 1600 for this particular type. Each time a failure is not resolved at design exit or during design test stage and each key checkpoint or milestone, we may have defects that are unresolved. So that allows us to then allocate scores on the resolution status of the defect. We would have, in this case, this one is like you see a score loss of showstopper of 11, a high major defect of 8, medium severity major defect of 5, and a low minor defect, clearly very low score of 2. Now, these are the severity scores. The resolution is dependent on how well understood these problems are. We have a problem understood, solution not defined and not demonstrated has a very high risk if we go forward or we ship products with that type of defect. Therefore, it has a 5-point resolution score. If the problem's understood, a solution has been defined by engineering but we've not demonstrated it, yeah, the risk is lower, but it still has a risk. In that case, it's 3 points. If it's analysed and demonstrated, then clearly we've solved the problem. There isn't a risk. Now, we are going to be showing you how to multiply the severity by the resolution scores to give us our overall score loss. In this case, we can see an example where we've got score loss per open issue calculated, as you can see below in that chart. We have, in this case, showstoppers, there's none. So we've got a rating of 11 in terms of its severity, but no defects. So there's no score loss for severity for showstopper ones. For a major defect that would result in customer rejection, we have 3 of these defects, and we have a less of a major defect with a 5 score severity rating. We've got 7 of them, and we've got 10 minor defects. Now, we then have to allocate the resolution levels to each of these defects, and we can see there for the 11 score severity we don't have any defects. We are scoring, we've got 3 of major defects with the high major defects with 8 point severity. These are all rated, in this case, having a 3 point resolution. So we have 3 times 8 times 3, or 72 points lost. Similarly, for the less major defects with a rating of 5, there are 7, but in this case all of these have a much higher resolution rating, and therefore more risks. So we have 7 times 5 times 5, or 175 points lost. We do the same for the minor, and you can see there's an overall points loss of 307. Our maximum score with our weighted scoring cumulated was 1600. As a result, we then see a maturity level of just over 80%. So that now becomes a measurable item that we can use going forward, and management engineering can talk about design maturity throughout the design cycle rather than just talking about number of defects. And it takes into account the different defects, the different severities, the different resolution levels, and we now have something very worthwhile for internal discussion. An example here where we're actually using score loss and we're taking data from it, and we have different stages of the design cycle, different faults found, different score loss, and we have different maturity levels, and we can see that, we can show it through gross maturity, we can set targets, and it becomes a very meaningful way to run the business in a design. We also see, as we work through this, different product types. Design maturity measurement is a great tool to look at how we improve new product performance in terms of design maturity, bring in strong lessons learned program, and how we can stage by stage improve our design maturity. Examples here where we see different products of the same type, different models. First mass production, very different. First release, as we start to basically improve the product. If we do the different modifications to solve the open issues, what would be the design maturity? It's a great way to talk about design quality and have an objective measure that people all drive. If we see here, we can see examples. The success of continual design quality improvement is clear. We can see first 30-day very infant mortality failure rate is coming down over a 3-year period. In the same time, in the same period here, we can see the 12-month warranty failure rate is coming down from 6% to just to 2%, and even less moving forward. So all of this is related to design maturity improvement. We can see, as a field failure rate prediction tool, we can get pretty good correlation if we are doing our design measurements correctly and we're using the right type of sensitive scoring in our design quality test program. Percentage design maturity against our 12-month field return rate or warranty failure rates. We can plot the data, we can fit a model to the data, and then ongoing, depending on what our maturity model is, we can then relate that and predict our field return rate in the warranty period. Clearly, there are products which are much more complex and have many more tests, and we can see examples here. We've got so many tests, both stress testing, functional testing. We can see the maximum scores are extremely high. We can see how we record defects. All of these defects will get allocated scores for their resolution, and etc. That data, we see the chart output. Very, very simple, but very efficient. Different charts, we can see different examples. And at the end, our design quality test failure output can be used for formal lessons learned. Right? Similar family model benchmarking can be easily performed within R&D. We've got gross design maturity levels will reflect improving designs. We can use this information for internal and exit review. Lead engineers can explain design quality corrective action records, what they've learned from improving designs to improve design quality issues. And this way each R&D team learns lessons. The design quality engineer is a key part of this. Design quality maturity levels will clearly show if the teams are learning quickly enough, year on year, product by product, and field failure data will clearly reflect the level of learning and their improvement levels. I'd like now just to finish this presentation, and effectively we will happily take questions, emails, etc., and we'd be more than happy to go into this in more detail with anybody who was interested in this. Thank you very much.